Let f be a function whose second derivative is given below. The points at which the first derivative equals 0 are x equals -3 and x equals +3 and x equals 0. Use the second derivative test to determine if these points give a relative maximum, relative minimum, or if the test fails. I like this exercise. This exercise really gets at the root of what this second derivative test tells you, without having to go through and find the first derivative and the critical values and finding the second derivative to plug the critical values into. You are given the second derivative here, which is 2x times the quantity x squared minus 27, all divided by x squared plus 9, the quantity cubed. So we already know the second derivative. We already know the critical values were given to us up here in the description. That's all we need to use the second derivative test. So what we know is if we find f double prime of c a critical value and it's bigger than 0, then there's a relative minimum because this is concave up at that particular point. And if you find f double prime of c and you get something less than 0, that gives you a relative maximum because this is concave down. And if f double prime of c equals 0, then the test fails. And if the test fails, since you didn't go through and find the first derivative from the original function and the critical values, we can't do anything here. Normally, the second derivative test states that if you find the second derivative and it equals 0, you have to go back and use the first derivative test. However, we don't have a first derivative to use, so we can just state that the test fails. When you go through and try to evaluate whether or not the second derivative is positive or negative, especially in this example, you just want to use a little bit of sign analysis. So I know if I substitute 3 into this function, I will have 2 times 3 times 3 squared minus 27 all over 3, not x, 3 squared plus 9, the quantity cubed. And what I see when I see something like this are signs. So I know the 2 is positive, I know the 3 is positive, and I know if 3 is squared and then you subtract 27, this will give you something negative. In the denominator, since the 3 is being squared and getting 9, 9 plus 9 is positive, a positive number cubed is also positive. So we have a positive times a negative, all being divided by a positive. That will give you something that is negative. So we can conclude that f double prime of 3 is less than 0, it's negative. You don't have to know the exact value. You just have to know if it's bigger than or less than 0. So we know that this is concave down and gives a relative maximum at x equals 3. And again, normally you would go through one of these exercises and substitute this 3 back into the original function to find the y coordinate of that relative maximum. However, we don't have the original function to substitute this value in. So we just have to say that there's a relative max at x equals 3. And if you follow this same logic for the other two values that are listed up here, 0 and -3, you will see that the f double prime of 0 is equal to 0 and f double prime of -3 is bigger than 0. So using the second derivative test over here on the right side of the screen, since the second derivative of 0 gives 0, that means the test fails at x equals 0. And since the second derivative at -3 is bigger than 0, that means it's concave up. That means there's going to be a relative minimum there. Rel min at x equals negative 3. So given the information that we have, this second derivative and the critical values, all we can say is that there's a relative max at x equals 3. The test fails at x equals 0, so you'll have to go back, if given more information, to use the first derivative test to see if that's a max or a min. And there's a relative minimum at x equals negative 3.